So I'm hoping that from now on we won't have any problems with the recording. I finally figured this software, and everything will be smooth, I hope. Okay, so let's make a quick review of our last lecture. On Friday, I talked about air pressure. First, I defined what a gas is, or what property makes a substance a gas, and then I said that any gas, due to its property, can fill up any container, and the gas molecules are in constant motion, and as a result of that, they constantly hit any surface within their path, and the collisions create a force on the walls of the container, and the sum of all tiny forces created by each individual molecules constitute the pressure force. Okay, and normally if you have a gas, the gas applies the same pressure everywhere, just because the motion of the molecules are random. So this is supposed to be a pen. It doesn't really look like it, but anyway, normally if you have the same pressure at every point, but things start to change whenever there is motion, and that's how the dynamic force is really created. So what you see here is what we call an airfoil. This is basically the cross section of an aircraft wing. When the aircraft wing is in motion, it has a certain velocity. This V represents the speed of the aircraft. There's another way to view this, and that is, if you are fixed to the aircraft, then you will see the airfoil as fixed, but instead you will see air flowing through your airfoil, and due to this special shape, the flow passing through the upper surface needs to get squeezed here, and then that results in an increase in the speed of the flow, and as a result of that, we get a pressure difference between the upper surface and lower surface, and this pressure difference creates a force in the upward direction, which is what constitutes the lift force. Okay, so this is basically what we discussed on Friday. So let's come back to today's lecture. Here I'm starting with the same concept of pressure, but now I would like to show you how the speed of an aircraft is measured. Okay? So here we see a box full of air, and these air molecules are in constant random motion, and just like they hit the walls of the container, they hit any device within that container, right? So let's consider these red lines here. These red lines represent force transducers. In other words, these devices can detect force applied to them, so they can measure pressure, in other words. So when you have this thing here, this will measure the pressure because it will be getting hit by air molecules. Okay, so if the air is steady, that means when there is no motion, a pressure transducer will measure the same pressure at every orientation. If there is an airflow, then the transducer measures a different pressure depending on its orientation with respect to the flow. So let me tell you what I mean by that. Okay, here we are considering a flowing air. Okay, so this is the average velocity of the flow. So that means every air molecule is moving with a velocity that is equal to the vector sum of its random velocity plus the velocity of the flow. So at this point, it matters how you orient your pressure transducer in the flow field. Okay, so the direction of the flow is this here. So if you place a transducer parallel to the direction of the flow, then this device only measures the static pressure. So let me just add a few words here to explain it better. Okay, so this sensor only gets hit. Bunu görebiliyorsunuz değil mi büyüklük olarak? Okay, so this sensor only gets hit due to the random motion of the molecules and not due to airflow, because the airflow is parallel to that, right? The velocity component due to airflow doesn't cause molecules to hit the transducer. They just pass parallel to it. So let me move it here and make it bigger. That means it only measures static pressure. And let me make sure that I'm talking about this sensor here. Okay, whereas if you consider this other sensor, this is placed perpendicular to the flow direction. This gets hit due to the random motion plus due to the motion of the flow, motion of the mean flow. That means this gets more collisions, right? And naturally that will detect a higher pressure. The total pressure so let me add this sentence there. This sensor gets hit due to the random motion of the molecules and due to airflow. There are more collisions and pressure is higher. This measures the total pressure, static pressure, plus the additional pressure due to airflow. Okay, so you have two sensors. One is placed parallel, the other one is placed perpendicular to it, and they measure different pressures. And the reason they measure different pressures is there's a flow. In other words, when there's no flow, both of them will measure the same pressure, and there will be no difference basically between those two measurements. But if there's an airflow, then there will be a difference, and the magnitude of the difference will depend on how fast the flow is naturally. Okay, so this is the idea behind how you can measure the speed of an aircraft. And this, okay, so let's read through this. In such a case, the transducers placed perpendicular to the flow direction will get hit by more particles compared to the transducers placed at an angle. Rather than at an angle, let me say it compared to the transducers placed in parallel. Transducers placed perpendicular to the flow measure the total pressure. When there is no flow, total pressure is equal to the static pressure. And total pressure increases as the speed of the flow increases. By comparing the total and static pressure measurements, you can estimate the speed of the flow. And this is how an aircraft speed is measured in a pitot-static tube. Okay, so these pictures shows diagrams of how a pitot-static tube design is. So this is the tube. So you have a hole here, and this hole is perpendicular to the flow. So the air going into this hole gives you the total pressure. And you have these two holes here, and the openings here are parallel to the flow. So the air going into this channel can do so only due to the random motion, which gives the basic static pressure. and these two measurements are compared inside. In fact, mechanically you can, this is how it looks like inside an airspeed indicator. The two pressures, the diaphragm here and the diaphragm will move with respect due to the pressure difference, and the motion of the diaphragm is converted into the motion of the needle here, showing the airspeed. Okay, so this is how you measure the speed of an aircraft. This is a very crucial information, by the way. I mean, if you're flying a small airplane, you may think that the accuracy of the speed measurement may not be that crucial. But there are certain cases when you need to know the speed very accurately. One example is if you are flying at night, and if you are flying over ocean, for example, there will be no light source, and if there is no moon, you can't possibly see anything around you. You will be flying in complete darkness. And in that case, you have no reference. You cannot judge your speed, right? So you have to rely on what your sensor shows you. And if that sensor shows you are flying slowly, then that's your only information. Or now most modern airliners, well, all modern airliners have autopilots. These autopilots control the airplane when the pilots do not need to manually control the airplane at all times, right? When you are flying from Istanbul to United States, for example, the flight takes more than 10 hours, and during the 10 hours, the pilots do not need to control the airplane at all times. The autopilot does the job. And in that case, for the autopilot, these measurements are crucial. And even in today's modern aircraft, still there are accidents due to these the Pitot Tube errors. And in fact, you must remember this Air France crash in Atlantic Ocean. It was, I think, like 7 or 8 years ago. It's a pretty recent crash, and that crash was due to a malfunction in the pitot-static system. The entire aircraft crashed, and 228 people died in that accident. And the only reason was the pitot-static system was not working properly. Let me show you some pictures here. So here you see some pitot-static tubes here, and the pilot here, or the co-pilot, is taking the mask off. I think this is before the flight. So you have to make sure that these tubes are very tiny tubes, and they're clean always, and they are free of water or ice. So these are really very sensitive devices, and you have to really take care of them. Modern pitot-static systems have heaters, so to prevent ice accumulation. But even then, like some small insects can go in there, and that can cause an entire aircraft to crash. Okay, so this is for the next. Okay, so let's continue before I talk about that picture. Okay, so again, this speed information is really critical, and you can measure the speed by comparing the total versus static pressures. And what's important is you measure the speed of the aircraft. And for that, you need to place the pitot tube carefully. So I think I can insert a new page here. Okay, so here's your airfoil, and you have your aircraft is flying with some speed v, and at a distance sufficiently far away, there's this uniform airflow, okay? But this airflow gets distracted or disturbed by your aircraft. That means if as this flow comes closer to your aircraft, it will be changed due to the geometry of your aircraft, right? So, for example, this the flow will be deflected upwards here. This flow here will be deflected downwards. The direction will be changing, and also the magnitude will be changing, right? So we know that the flow will be accelerated here. So this, let me call this VU. This is greater than V, and flow here will be decelerated. Let me call this VD, and this will be less than V. But you don't care about what VU is or VD is. For the reasons I mentioned earlier, what you care about is this velocity. And this is called the free stream velocity. Okay, so let me cut this definition and paste it here. So the free stream is the air far upstream of an aerodynamic body before the body has a chance to deflect, slow down, or compress the air. And because of that, the free stream velocity is denoted with a sub-symbol of infinity. So we call this V infinity. That means the speed of the flow that is sufficiently far away from your aircraft. So this is what you want to measure, right? You want to measure the speed here. So because of that, you need to place your pitot tube carefully. If you, for example, put a pitot tube here, that will measure the speed of the flow here, or if you put it here, it will measure a different speed. So for that purpose, you try to place the pitot tube in a place where the flow is least distracted by the aircraft. So let's take a look at some sample placements. So for example, here they put it underneath the wing, but it's extended forward a little bit. So the idea is that the effect of the aircraft geometry is less there. Or for fighter aircraft, they put the probe at the nose, like this one, for example, or or there's one here. It's hard to see. So these are the places used for aircraft typically. But even then, you cannot really make sure that the local flow there is the free stream flow is equal to the free stream flow. So what they do is they calibrate these sensors. Okay, so the sensor here, for example, you cannot claim that the flow speed here is equal to the free stream velocity because it's already flowing around the fuselage here. So obviously it's distracted, but these things are calibrated, and to do so, they take measurements with other sensors that give more realistic data. And this is a device used for such a purpose. This is the F-16 aircraft. So they place this additional sensor to the front, and this sensor here gives a better measure of the free stream velocity. And this is the other sensors used, for example, right? You have these other sensors here. So you put a device here, and you say that this should be the correct measurement. You take measurements from here, and you compare them, and then you make a calibration table for these sensors. In other words, if you see a measurement here, you compare it with the other data, and you say that if I measure this value here, the actual flow speed must be this. And that's how you obtain these calibration tables, and then you use them. So even though you know that you don't have free stream conditions here, using these calibration tables, you can get a better estimation of the real free stream velocity. Okay. Let's see. So I think this is pretty much all I want to say about a pitot-static system. So we can move on to this next topic. Now we are starting to talk about forces in more detail. So far, hopefully I convinced you that when there's an airflow, if you place a carefully designed airfoil into the flow, you can get some forces. And now we will be talking about how we use these forces for our engineering calculations. Okay, so since we are assuming that all the forces are created by an airfoil, it's a good idea to start with some parameters defined to describe the shape of an airfoil. So the airfoil is the shape of an aerodynamic force generating surface, such as wing. We will be considering wings, but wings are not the only force generating surfaces. For example, a propeller blade is also called an airfoil because the propeller is used to create a force, aerodynamic force. The propellers are used to create the thrust force, but the thrust force comes from the way the thrust force is created is very similar to the way the lift force is created on a wing. The shape of the aerodynamic force generating surface is seen in cross-section obtained by intersecting the wing with a perpendicular plane. So basically you cut a slice of your wing, and if you look at the cross-section, the shape you see is called an airfoil. So just like the wing planform, to use airfoils in engineering calculations, we need to define certain parameters that describe the shape of an airfoil. The chord line is defined as a straight line connecting the leading edge and trailing edges of an airfoil. So the leading edge is the frontmost point, the trailing edge is the rearmost point. If you connect these two lines with a straight line, which is this red line here, you get the chord line. The mean camber line is a line drawn midway between the upper and lower surfaces. Okay, so the red is your chord line, right? Then you draw this black one is your airfoil. Then you draw a perpendicular line to the chord line, and the midpoint between the upper and lower surfaces is where the mean camber line passes. So you do this for the entire airfoil, and then you connect all the midpoints. That will give you this blue line, and that blue line is called the mean camber line. So that's the midpoint of your airfoil. So this note says that for a symmetric airfoil, the chord and mean camber lines coincide. So the symmetric means symmetric with respect to this x-axis here. So if the x-axis is defined here, and if your airfoil is symmetric around this axis, then your upper surface will be a mirror image of the lower surface, and hence the midpoint will be passing through the x-axis. And in such a case, chord lines and mean camber lines will be the same. Chord is the length of the chord line. We use the small case letter C to represent the chord line, the chord length. And camber is the distance between the mean camber line and chord line. So the mean camber line is the blue line, chord line is the red line, and this distance is called the camber. And as you see, camber is not a fixed number. The distance between the two depends on where you measure it. So if you measure it here, the distance is 0. But if you measure it here, there is this much distance. If you measure it here, the distance is greater. So the camber is a function of x, basically. The camber changes along the chord line, it's a function of x. Okay? So by the way, does anybody know here the Turkish term for camber? Efendim? Duymadım ama Türkçesi kambur. Güzel bir kelime değil mi? Bayağı yakın. Okay, so this is how you define. So remember, this curvature is crucial in creating lift force. So camber is really an important property of an airfoil, naturally. Then the next thing is the thickness. Oh, by the way, the camber is usually represented in terms of, not in terms of the actual distance, but in terms of the ratio of that distance to the chord line. So here, if the chord length is 1 meter, and if the camber is 5 centimeters, you don't say camber is 5 centimeters. Instead, you say you have 5% camber, because that's the ratio of the camber to the chord line. So by the way, aerodynamics people love these non-dimensional numbers. So everything you can think of is somehow non-dimensionalized. So if you are talking about an area, you divide it by another area and it becomes a unitless number. Or if you have a distance, they divide it by another distance and it becomes again a non-dimensional number. So I will be more about this non-dimensionalizing. But this is done very frequently in aerodynamics. Okay, so let's take a look at the thickness. Thickness is the distance between the upper and lower surfaces. Again, usually presented as a percentage of the chord. And just like camber, thickness of an airfoil also changes along the chord. That's also a function of x. Right? So similarly, the thickness here at the nose is 0. You have a little thickness here, and the thickness gets larger. At some point, the thickness is the most. You have the thickest point of your airfoil, and then it gets smaller, starts getting smaller again, and then finally at the trailing edge, it drops down to 0. And the camber and thickness information is sufficient to draw the airfoil. So if you know the thickness and camber, you can draw the entire airfoil. Or if you know the upper and lower surface coordinates, then that will also give you the entire shape, right? So you can either know the upper surface and the lower surface and put together, that will give you the airfoil shape. Or instead of knowing those two, if you know the camber and the thickness, that's the same thing. You can get the entire shape using those two as well. So I'm looking for a point where we can take a break, but I don't know, it just keeps going. So I talked about V infinity already. This is the free stream velocity or the speed of the aircraft. They are the same thing if there are no winds. But if there's a wind, there will be a difference. But if you assume that there are no winds, atmosphere is stationary, then your speed, the aircraft speed will be equal to the free stream velocity, but in the opposite direction. Okay, now next comes a very important angle called angle of attack. So this is a very, very important angle, and hopefully nobody passing this course will, well, or I should say, everybody passing this course should have a very clear understanding of what angle of attack is. So it's very easy to get confused. Even though the definition is really simple. If you know the definition, then you will have no confusions. But for some reason, students will get problems finding angle of attack in different flight conditions. So anyway, the angle of attack is defined as the angle between the chord line and the free stream flow. The Greek letter alpha is used to represent angle of attack, and it is positive if the flow is coming below the chord line. So I guess I already talked about this part here. We can. Okay, so here there are some cases showing the angle of attack. So excuse the quality of the pictures. I know that the drawings are not really nice, but I guess you can understand what I'm trying to show here. So this is an airfoil, the green one, and this black line here is your chord line. Okay, so this is just a straight line, and this is your free stream velocity V infinity, your V infinity vector. And in this case, the angle between these two lines is your angle of attack. Okay, and it's shown here. This is your angle of attack. And in this case, this is a positive angle because the flow is coming under the chord line. Okay, now let's take a look at this case. The flow direction is the same as before. It's still horizontal. But this time, the chord line is oriented in this way. This is the underside of your airfoil. But the airflow is coming towards the upper surface. So that means the angle between them is angle of attack, but this is a negative angle. Okay, so this is less than 0 angle of attack. So I wish I had an aircraft here to show. Maybe I can take one in the break. Okay, so in this case, the V infinity vector is horizontal. That means this is your flight direction. The aircraft is flying horizontally, but the leading edge is pointed upwards. Okay, in here, the aircraft is again flying horizontally, but the leading edge is pointed downwards, and this is a negative angle of attack. Here, your free stream velocity is this vector. So if air is coming through this direction, that means your aircraft must be going in the opposite direction. So this shows a climbing aircraft, right? Your aircraft is flying through this direction, and the chord line is horizontal. Here's the angle of attack, the angle between the two lines. And since the flow is coming towards the upper surface, this is a negative angle of attack. And in this last case, the chord line is horizontal again, but your free stream velocity vector is this vector. So in this case, the aircraft is descending. Your aircraft is moving in the opposite direction. It's going down. And since the airflow is coming towards the lower surface of your airfoil, you have a positive angle of attack. Okay? So again, the definition is really simple. If you keep this in mind, you will have no problems. But yet, whenever I show a question like that in the exam, most of the time students get confused. And let me see if I can show you a sample exam. This was not here. So by the way, I will give you all these exam questions. I will give you all the exam questions I have that I asked in previous years. So you will have these exam questions to study before the. Okay, so I was talking about this, for example. So here, in this question, I asked you to find the angle of attack. And believe me, many students didn't get the answers correctly in this question, even though if you think about it, there's really nothing to confuse. So I give the directions of the free stream flow, and this dashed line here represents the chord line direction, and you can easily find the angle of attack. Okay. So I feel like we're going really fast when I read through these slides. So that's why I'm trying to slow down as much as I can. Because if this was a regular class where I was writing all this stuff on the board and you are taking notes, we wouldn't be able to go this fast. Okay, so let's start these aerodynamic forces. Aerodynamic forces are created by the pressure distributions over the bodies. Every part of an aircraft exposed to air is under pressure and hence contributes to aerodynamic forces. But as I said, we will be ignoring the forces on other parts and we will look at the force on the wings only. But in reality, obviously, the other parts contribute to forces as well. And because of that, you have to be very careful to hide everything else so that their contribution will be very small. This is why you retract the landing gears during flight, or the nacelles and pylons are used to make various components aerodynamically efficient. So let me show you some. Bunlar da pylon deniyormuş herhalde. So anyway, whenever you have there's something sticking out of your fuselage, you have to hide it with very nice, smoothly shaped surfaces, such that the air flowing around it will not give you too much trouble. So this is a better picture of the pressure distribution. Before I drew this manual with my hands, and this is I did this drawing myself, but I was more careful doing that. So when there is no flow, you have the same pressure everywhere. So these blue arrows have the same length. All these blue arrows have the same length, meaning the pressure force is the same everywhere. But when there's motion, things start to change. Okay, so here is the thickest part, and naturally the flow will be accelerated most while passing through this part, right? That means the pressure here will be the lowest. So that's why you have this green arrow here, which is shorter, much shorter than the blue arrow here. And so obviously this depends on, again, how fast the flow is. If the flow is very small, then the difference between green and blue will be very small. But as the speed is increased, then the difference will be getting larger. So by the way, these arrows can never be negative, right? So there's no such thing as negative pressure. So by definition, pressure is always a positive force, because the molecules hit the surface and create a force, and that force is coming towards the surface is the positive direction. So there can at most be no pressure force, but you cannot really have negative pressure force. So the best that can happen is this green arrow becomes zero length in the ideal case, but other than that, you cannot really have a negative pressure. Okay, so the pressure difference occurred due to the flow. Due to flow is the difference between the green distribution and blue distribution. And this difference can be found by overlaying the green distribution on the blue one and then subtracting the blue distribution from the green one. So we can do this graphically. So in the no flow case, you have this blue distribution, but whenever there is flow, you have the green distribution, and the difference is represented by these red arrows here. So I'm subtracting the blue one from the green one. So here I have this little red arrow. Here I have a slightly larger red arrow. Here the arrows are in the other direction because the green one is smaller. And when you plot the red lines, this is what you get. So if you look at here, you see these red arrows are pointed from the airfoil, and this may seem like a negative pressure, but that's not really. That's only the relative pressure with respect to the no flow case. Okay, so that's why you have that arrow in the other direction. Other than that, it doesn't really mean that you have negative pressure. So here in our last lecture, I told you that you get the pressure difference. So this red picture is a much more realistic picture showing the actual pressure distribution. Okay, so when there's no flow, adding all these blue curves will give you no force. But if you have flow, you have such a pressure distribution, and adding these red arrows will give you something. They don't cancel each other out. You see this one doesn't cancel this. In fact, they add up and you have a force in that direction. Okay, so let's just give a break and I will continue after the break.